Okay, I think let's continue with part two. So in the first half, we saw just the noise channels and noisy gates, readout error mitigation, and some basic noise learning, right, of the Pauli noise channels. We just looked at several sources of noise and the need for error mitigation, and a high-level overview of some of the algorithms, basic concepts such as Pauli transfer matrices, Pauli channels and twirling, and that's the readout error. So then we also saw that how you can learn Pauli noise in the context of Clifford gates, and how you do that by just learning the fidelity at different numbers of repeats and fitting an exponentially decaying curve through it. So in the second part, we'll look at probabilistic error cancellation, zero noise extrapolation, and coherent Pauli checks. So for probabilistic error cancellation, or PEC, so we saw that we can represent the Pauli channel by its Pauli transfer matrix will be just the diagonal of the fidelities, right? And we also saw that if you have the Pauli transfer matrix of two maps, that's just the product of the Pauli transfer matrices of each of the two maps. So if the noise inverse map exists, then clearly the Pauli transfer matrix of the inverse noise map, it must be the diagonal of the inverse fidelities, because if you multiply two diagonals and one is 1 over f, the other is f, then obviously that will go to the identity matrix, which is exactly the inverse of the noise. So we saw also that you can switch between the channel coefficients, the probabilities, and the fidelities using the Walsh-Hadamard transformation. So suppose we're given this Pauli channel, right? So it has an identity term x, y, and z, and we just put all of the probabilities in the vector, right? Then if we pre-multiply this by the Walsh-Hadamard, we just get the fidelities of this channel, and then we can just invert them. So we just 1 over the fidelity, that would be the inverse fidelities, let's say. And then if we apply the inverse Walsh-Hadamard to this, we get our new quote-unquote probabilities, right? So this will be the channel coefficients, or it's actually a map. So the inverse map can be written as this 1.19 times rho minus something. So it's not the physical channel, but it's just a map, right? So this is just the inverse noise map. And if you want to implement a normal Pauli channel, you can just sample terms with a certain probability and apply them. But here we get negative probabilities, and some of the probabilities, if you like, are larger than 1. So that's a bit more difficult to work with. The solution here is just to implement this quasi-probabilistically. So the first step to process this is to just associate a sign with each term, right? You just have the non-negative coefficient. So you have 1.19 that was here, but here we have minus 0.07. We just say this is 0.07 times the sign of x, will be -1. And then you just have your x term here. We can then renormalize the coefficients by the summation of these terms to then turn this into a probability of the different terms. The terms may still have a sign here, and there's an overall scaling factor there. So we can now sample each of these terms independently. But what we do still have is this sign, S, and our scaling factor gamma, right? But this kind of procedure is usually used in the context of estimating observable values, And of course, if we just calculate the observable values, we can easily multiply by -1 or scale it by gamma. So this is how we then implement it. So we just apply those classically. So if you apply PEC to implement the inverse noise map, right? You just implement it. That does mean you have to scale your observable values with this gamma parameter, right? Normally, the variance in some observable expectation values scales as 1 over the number of shots, right? So if you take a lot of shots, then the variance in your expectation value, empirical one, that just decreases. But if you then scale by plus or minus gamma, you increase the variance by a factor of gamma squared, right? And to then just get this back to the original level based on the number of shots, you need to take gamma squared times the number of original shots. So that's the cost you pay for inverting this map, right? Just to get around the non-physicality. Now, Pauli channels, as we've seen, are easy to work with. So for an n-qubit channel, we have 4 to the n coefficients. So this does not scale. So if you want a scalable approach, you need an even more structured model. And in this work, we introduced such a model. It's called the sparse Pauli-Lindblad noise model. And the assumption here, that's just an assumption, is that you can write your noise channel as just a time evolution of a Lindbladian, right? With the Lindbladian just being the sum of this lambda k times Pauli k terms here. This is just the dissipative part of the Lindbladian. There's no Hamiltonian part. Yes, just the dissipative part. And because we just consider the diagonal terms here, these Paulis, they just change to the identity. This operator, if we have A and B, is just A times B plus B times A. This is identity, so that's just the same. That turns into this expression here. Right, that's the Lindbladian. If you work out this time evolution or exponentiation, you get your noise channel is equal to this operator. So apply this on the next one, where each of these terms here is a tiny little Pauli channel. You have some weight times your operator, 1 minus weight times the Pauli applied to this. I don't put rho here because you need to sort of multiply these channels together. It's one Pauli on top of the other on top of the other, and you apply that whole thing on your state. These W's here are just 1 plus e to the minus 2 lambda k over 2, where lambda k is chosen to be greater or equal than 0 to make it physical. So the original noise channel is assumed to be physical. So this is actually just a product of commuting simple Pauli channels for k, where k is just a subset of the Pauli group, individual terms. So either you do nothing or you apply a Pauli. That's one channel. And then the next channel has the same, but you apply another Pauli. So if you have a single qubit channel and your set k is Pauli x, y, and z, then this would just be some Pauli channel x, some Pauli channel y, some Pauli channel z in arbitrary order because they commute. Right? So the model in that case is just defined by which Pauli terms do you include in your model and what are the associated parameters lambda. So if we restrict this set k to be small, then we get the sparse or scalable noise model. Right? Now, just because this set is small does not mean that the expansion of this whole channel will be small, because that sort of does the convolution of all the Pauli terms. So combining the channels may still give you a very large Pauli channel. So So that's less structured. You can still get some complicated diagonal fidelities. So how do we choose the Pauli terms in the model? Here's just a number of qubits in some topology. What we do is we choose K as the two local Paulis that follow the topology, right? So that's pretty much linear in the number of connected qubit pairs. So here we have, I think, 11 qubits. The weight 1 Paulis on each qubit is just x, y, and z. So we get 11 qubits times 3 terms. And then there's 10 edges. Each edge has x, y, z times x, y, z. So that's 9. So that's another 90 terms here. So in total, these 11 qubits would have 123 parameters. If you compare this with the explicit Pauli channel, which has 4 to the 11 minus 1, that's of course much larger, right? So this is a much sparser representation, but as I mentioned, these local low-weight Paulis can still combine into high-weight Pauli errors, but the probability is just very small. Okay, so the main question, any questions? No? Yeah.
I was just maybe not sure how you got the 4 to the power 11 minus 1.
That's right.
The expression for the number of parameters for the full Pauli model, how did you get 4 to the power 11 minus 1?
Oh, because for a Pauli channel, right, you have all of the possible Paulis. And on each qubit there's identity x, y, and z. So all of the strings over this alphabet is 4 to the n. And then you can say, well, minus 1 because the identity I know. But yeah. Okay, so if I'm given, or if I give you the set K, which Paulis to include, how do we learn the model parameters? And for this, what we do is we just look at the fidelity of some Pauli term under this noise model, right? So if lambda is the noise, what does this trace look like? And it turns out that this is given by the exponential of minus 2 times all of the elements in K times the symplectic inner product between our target Pauli B and our element K. So this is just, the symplectic product will be 0 if the Paulis commute. If they anti-commute, it will be 1. So this is the sum over all of the terms K that anti-commute with B of lambda K. Okay. Now, if you just take the logarithm on both sides, just assuming that the fidelities are not negative or 0, with just a reasonably good fidelities bounded away from 0, then the log fidelity is just the sum of these terms, and these are fixed. It's just 0 or 1. We know B, we know the set K. So this is just a weighted sum of the lambda parameters, right? So if we choose some subset of Paulis that we want to measure the fidelity for, and we stack all of the fidelities in a vector, then we can write some matrix that depends on the set B and the set of K of model terms. That's just a binary matrix. Times our lambda should be equal to minus log of the fidelities over 2. This should just be FB. So that just gives us a system of equations we may want to solve, right? But we also want to make sure that the original channel is physical, so we want to have lambda non-negative, right? So if we're given some estimate f hat of this fidelities, well, we just solve a non-negative least squares problem. This is just the least squares, right? So m times lambda is minus log f, right? So we just subtract negative log f. That just adds it. Just a 2 norm squared scaling factor for convenience and non-negativity of the parameters. Okay. And the solution of this problem is unique whenever M is full column rank. So there does not exist a non-zero lambda such that M times lambda is 0. right? If you choose your elements B to be such that this matrix is full column rank, it can be a tall matrix, then we can solve for lambda. So we can have a redundant number of fidelities to measure. So in the paper I showed earlier, it suffices in that case to choose B equal to K. Then this matrix will be square and it will be guaranteed to be full column rank. So we know how to choose this, and we've seen how to measure the individual fidelities. So that means we can actually solve for the model parameters. So now we're in a situation where we actually have a product of these simple Pauli channels, and we can invert them individually because all of the Pauli channels, they commute, and the inverses is also has a diagonal Pauli transfer matrix, so that also commutes. So we can just invert individual channels. So if we have some simple Pauli channel with alpha rho plus 1 minus alpha p rho p dagger, then the inverse noise map has a similar form, so it's alpha times rho minus 1 minus alpha times p rho p dagger, plus some scaling factor of gamma for this particular little noise channel, right? So we can then implement this by sampling a term from alpha or 1 minus alpha, right? And with the sign, we need to keep track of that this was a negative, and we have the scaling factor. So if we want to invert all of the channels, we just per channel sample something and just pre-multiply it with that term. So what happens is let's say the first term, we sample this Pauli, it has a weight -1. The second channel, it's component of the channel, we may sample identity, it has a +1, and so on. Now these are just all Pauli, so we can just multiply them together. The sign again doesn't matter here, so it maybe x times z becomes identity, imaginary y, or maybe minus. That doesn't matter. This sign does matter, so we get -1, that will be +1 in that case, right? So if we pre-multiply the channel with this, and that's repeated many times with these different weights we sample, and an overall scaling factor of gamma i's 1/2 alpha I -1, so we take the product of all of these, then we can just invert that noise map, right? Is that clear? Good. Okay. So that's just the basis of this sparse Pauli-Lindblad noise model. We just use the techniques described earlier to learn the fidelities. That allows us to form a linear system of equations that we can solve with non-negative least squares. And that gives us a product of simple Pauli channels, each of which is easy to invert. And we just sample terms from this quasi-probabilistic model. Okay, so let's look at an application. So here's an illustration of a circuit. It has layers of single qubit gates, as well as layers of non-overlapping 2-qubit Clifford gates. We focus mostly on the noisy layers of 2-qubit gates. We just assume that the single qubit gates are so much better than the 2-qubit gates that we don't worry about noise on them. So we just look at these terms here. So we start with some noisy layers of gates with the single qubit gates in between. We just split the noise channels, the noisy gates into the noise channel and the ideal gate. Apply the twirling to twirl everything to Pauli channel. So before each term, you just insert a Pauli before and after, where the Pauli at the end comes from the middle, let's say. We already had single qubit gates here, so we can just combine those Paulis for twirling into the gates that were already here, so that just remains a single qubit gate there. Then we learn each of the noise independently. or we learn the noise for each unique set of gates, and just invert the noise channel by quasi-probabilistic sampling. So this again, you would insert, you would sample a Pauli to do the inversion, and you just insert them into those single qubit Paulis again. So the structure will really be single qubit Paulis, layer single qubit operators, not Paulis, and then you just alternate. Okay, so one example here is just the trotterization of a 1D Ising model of e to the minus IHT, where the Hamiltonian, let's say of a chain, right? You apply an X Pauli on each of the qubits with some weight, and you have ZZ terms on neighboring qubits. So that gives you two terms of the Hamiltonian, and obviously they don't commute because X does not commute with Z, right? And the rest of the terms on this is identity and here as well. So they don't commute. Between themselves, any Z's commute, so that's not a problem, and X is the same. So if you want to do this exponentiation, you can just say, well, let's do a first order trotter decomposition. Right? We just write e to the minus IHT as a time evolution of the ZZ component and the X component, and we just truncate, we just divide the time into slices and just raise that to the power S. Now, the exponentiation of X is easy, that's just rotation gates. To implement the ZZ gate, you can apply a C0 on AB, then a rotation on the B qubit, and then again a C0. So for a single pair, you can write that as this combination. Here's the first C0, the rotation, and then the second C0. Now, for the ZZs, we need to do this for every pair, but if we do it on 1 and 2, then we cannot also do a C0 on 2 and 3 at the same time. So we split this in even and odd qubits, right? So this is just on, let's say 1, 2, 3, 4, etc., and this would be on 2, 3, and so on. So that gives us two unique layers. This is the first one, they're identical, and these are identical. And so we just need to learn the noise for these two layers. And then we can apply PEC on this circuit. So this whole block is just one element of this trotter decomposition, and we just repeat this S times to get our evolution. So we'll learn.
So
yeah.
For layer 1, for example, you're going to learn the noise for that entire layer, or
Yeah.
you're going to split it into 2 parts and learn the noises for the 2
We learn it
C0s.
for this layer, but then we assume that the noise for this
It's the same.
is the same.
Okay.
Yeah, it's just Markovian noise. Once we've done that, once we've learned the noise, we can just apply PEC for different values of S and just a fixed delta T. So we don't actually scale the delta T. It's sort of a way of doing the time evolution. We then compute the magnetization, so the average X magnetization of single qubit X observables, and the same for Y and Z. So as a function of S, just 1, 2, 3, etc., if you plot the values of the Z and Y magnetization, you get this dotted line. Well, it's actually just the points, but the line is just for visual representation. If you don't apply a PEC, so you just apply the circuit and you measure everything, the spiral tends to just go to 0 much faster than desired. If you do apply PEC, you see it follows the curve much more closely. And if you look at the relative Euclidean distance to the origin, without PEC, you get this error, and with PEC, you get a much smaller error. And this is still a fairly small example. Since then, the hardware has become a lot better, so we can now scale this much larger. Now, in terms of scalability, right? If we have k layers, and the first layer, let's say combined, has a overhead of gamma 1, the second one of gamma 2, then the overall scaling factor of the number of samples you need to take is gamma 1 times gamma 2 to the power k. So this scales exponentially fast. So this, of course, limits the size and the number of layers that you can mitigate with this technique. So let's just assume there's local 2 qubit depolarizing noise with some Pauli fidelity f. Then if you say, well, I have 50 qubits and I want to take 10, 20, 30 trotter steps, how many more samples do I need to take to get the unit variance compared to just sampling the ideal version? And you see that as the error increases, the number of circuit instances really grows dramatically, right? 10 trotter steps at this error rate takes 10 to the 15 shots, which is too many. So that looks really bad. But on the other hand, it also says that if your hardware fidelity goes down even a little bit, or improves a little bit, right? You go from 10 to -2 to -3, suddenly maybe 100 times more than before. So that means that now it becomes very much feasible in this region. So this is, of course, a known difficulty with PEC. The scaling overhead is exponential. So there's limitations of the method. Also, if you have a lot of different unique layers, you would have to characterize each of them, which takes a lot of learning time. If learning takes too long, by the time you finish learning, maybe the noise has already changed, because the noise does drift on these systems, so maybe on the order of hours.
I have a high-level question about this chart of the previous page.
Yeah.
How come that the errors on the x-axis and the number of shots is on the y-axis? Maybe it's just me, but I'm thinking of the number of shots as the independent variable and the error as the dependent variable.
Well, this is the fidelity of the gates, of the noise on the gates as they are applied in hardware, let's say, right? If the gate quality improves, then this scaling factor becomes much smaller. So there's less to invert, and that's why the shot overhead goes down. Yeah. Okay. Okay, so that's just how PEC works in this case. There's another way to look at it is if you want to represent certain noiseless gates as a linear combination of noisy gates, then you can apply the same quasi-probabilistic inversion to represent this. So we've seen how to inverse the noise channel and presented this sparse Pauli-Lindblad noise model, which is really seems to work really well. Even though the number of parameters is small, it does seem to capture most of the noise in the system, actually. So the number of coefficients scale pretty much linearly in the number of qubits. So we can really learn this for 100 qubit layer of CNOT gates. And we've shown how well it works on this small Ising model experiment. So if there's no more questions, I'll move on to, okay, yeah.
So, I mean, I get that you need to restrict to Pauli's to ensure a sparseness of the channels and scalability, but is there I guess a similar probabilistic error method where you can do it for linear combination of Pauli's? That's your noise channel?
So in the Lindbladian, you mean you want to choose different terms?
So, I mean, in the Lindblad approach, I guess you cannot do that because
the time evolution may become messy.
Yeah, but other probabilistic error methods where you can also, you can use other techniques for linear combination of Pauli's, for example.
Maybe, yeah, I don't know. But there's ways to, for example, implement noiseless gates based on noisy gates, as long as you can represent them as linear combinations. Yeah. Yeah. Question.
So I guess from the user's perspective, like you're basically saying, like you have certain patterns of C nods with learned noise,
Yeah.
and you want the users to just use those patterns, like as much as possible.
Yes. Well, I mean, if you would provide a very complicated circuit with a lot of different unique layers, because we really want to know the noise associated with one particular layer. If they're decoupled, maybe you can just learn them. But if they're very correlated, if there's crosstalk noise between gates, then if you have two C nodes or maybe you just have one, then the whole noise signature will differ. So it's really because the gates, they induce some noise as well, right? Or crosstalk. So that's why the noise is sort of unique per layer.
But like for example, if you have like this pattern and then what if I just remove, if I don't do one of the C nodes in that pattern? Is there like a kind of easy relation between this new configuration compared to the one you learned?
They will be somewhat similar, yes, but the crosstalk does matter, right? So those terms you would have to then isolate and then use it. Yeah. So there are some things you can do, definitely, but of course, if you just really want to learn the noise per layer, then the number of layers is somewhat restricted. Yeah. Okay, so let's look at zero noise extrapolation. This technique, conceptually, of course, it's just very simple. You evaluate the observable at different noise levels, right, and just fit the curve and extrapolate to zero, and that's it. That's our value. So how do you amplify the noise? How do you make it worse? So one original idea done in this paper here is you do gate stretching. So you just let's say you scale the Hamiltonian by some factor alpha, but you make it alpha times longer. Right? This should ideally implement the same gate, but of course there's dissipative terms in the Lindbladian, which maybe the T1, T2 terms, etc., that then act over a longer period of time, so your noise does increase. So by just scaling stretching the gates, you get more noisy gates. So this was used in this paper to get the ground energy of certain molecules. Yes, question.
Another question. If you like make the amplitude smaller, wouldn't you also be like decreasing the amount of like, let's say like AC stark shift noise you get as well?
Sorry, if you
Like if you like decrease the amplitude of your gate, like you would also like decrease the amount of like, let's say like AC stark shift noise that you get as well, right? Or like leakage to other energy levels.
Maybe, but I think it's not the dissipative terms in the Hamiltonian. They remain the same. They're not scaled by alpha, so they remain the same. But then you do evolve it over longer periods of time.
Okay, so you're saying that the dissipative terms are more dominant over the AC stark shift.
They will show up more because you don't really scale them down, but they do act over a longer period of time. Yeah. So that's one way to do this. That's sort of the original way it was done in the first experiment. But one difficulty, of course, it requires you to tune these gates with different durations. And maybe you want to make sure that every gate is stretched by the same amount, and you have to tune the amplitude to get the correct operation still. So that's somewhat painful, and it's difficult to control the overall noise level. Another technique is called digital Z&E. So it just says, well, I'm going to do, for example, unitary unfolding. There's several papers that do this. You replace U by U dagger U, this is just the identity, ideally, to the power k, and if you just assume some conditions on the noise, that would amplify the noise appropriately, right? So you can be a single gate, it can be a set of gates or a layer, or just the whole entire circuit. You do the circuit, you flip it, you just keep repeating it and just hope to amplify the noise properly. Identity scaling, so you can replace some unitary by just keep really applying an identity gate and hope that will make the noise worse. So several challenges of this approach is that it sort of gives you a limited number of noise levels. You can't really control it too well. If you're given some noisy gate, do you know what the noise will be for the U dagger? That's one question that's not entirely clear. And so if you apply this, how do you get U to the noise to the power 3? You kind of want to exponentiate the noise there. And in this case, that would require that the noise channel is invariant under your unitary. So let's say global depolarizing that, then it would work, but maybe that's not an entirely realistic noise model for a single gate, let's say. So this has some complications. But then we can go back to the PEC, the noise model, and say, well, instead of probabilistic error cancellation, why don't we just do probabilistic error amplification, right? So in PEC, we invert the noise by implementing lambda inverse, but we can also implement lambda to the power alpha, and that just is done by just simply scaling these lambda parameters by factor alpha. We did -1, but you can do maybe 2 or 3, so you can make it worse. So then instead of adding a lambda inverse, you just make things worse. And the first noise comes for free, so you have 1 plus alpha noise in that case, right? So probabilistic error amplification actually matches the Z and E structure very well. You have very accurate control of the noise level. You really know how it scales. Unlike error cancellation, where alpha is less than 0, if alpha is greater or equal than 0, there's no sampling overhead because it stays in a Pauli channel. And if your circuit is Clifford, then your noise exactly scales exponentially. So your observable values really scale according to an exponentially decaying curve, which means that extrapolation would actually be exact in that sense. So this technique has been used to show quantum utility on a 127 qubit example in this work by the IBM group. So that was sort of C&E. C&E is sort of such a simple technique. There's not many slides on it. So yeah. So remember that if we had the Pauli channel or the Pauli inverse channel, we sample one term. So here we again sample a term and just insert it as noise. So that's the probabilistic part. And if you want to amplify the noise, you just really sample from a Pauli channel, and that means there's no gamma overhead, it's just 1. Yeah. Okay, so then the last topic, let's see, a lot of time. Coherent Pauli check. So this is just based on joint work with colleagues at IBM. So coherent Pauli checks can be used to check for errors during the execution of some Clifford circuit. Again, we're restricted to Cliffords for reasons I'll show later. So given these checks, you can do post-selection. So you check the outcome. If you say this is not correct, you just throw it out. And just get a better distribution of the sample. So it's one step closer to error correction, but it's just detection. So this way you just get a more reliable distribution of your samples. So this is per sample. It's better. It's not necessarily used for observable values. So how does it work, right? So given any Clifford circuit or operator U, we can choose any Pauli and just add 2 Paulis before it, right? If they're noiseless, let's say. Because L times L is just the identity, I've not really done anything. And then we've seen that we can push Pauli gates through Clifford gates. So we can just push L to the other side and we get some Pauli R on the right, right? That's just conjugate L with your operator U. And so you can just extend this construction. Here we have a multi-qubit system. We apply a check qubit, which is initialized in 0. You apply Hadamard gates and 2 controlled Ls. Okay, so these still cancel, so ideally we've done nothing. But now we can again push one of these Paulis through to the other side. So we get now a left check, a unitary, and a right check in this circuit. And what happens if there's some error in the unitary, let's say, and we propagate it to the end of U, then it might propagate as follows, and then we measure a 1. So normally we should measure a 0, but now we measure a 1. So we detected that there was an error. So if an error at this point anti-commutes with R, then that will show up as an error and we can detect it, and then we can just ignore that shot. We say this was not a valid shot. So you can post-select and filter it out. And this idea has been used in several papers before we looked at it. So what does it mean to have a multi-qubit controlled Pauli gate? So we just had the left check here. Yeah. Oh, we'll get to that. Yeah, we'll get to that. So this is just, let's say, a controlled X, Y, I, Z term, right? This just decouples. So you have a controlled X, you controlled Y, controlled identity if you really want to do it, but you can just omit it, and then a controlled Z term. So that's how you can implement them. So you can add multiple checks, right? So you have maybe 3 check qubits, and all of them should be 0. One is you just apply left 3 and right 3, and then there's a second one, an outermost one, left 1 and right 1. You can even actually just see this whole circuit we had here as a new Clifford circuit and apply a whole check on the whole circuit if you really want to, but that's not what we've done. So every check sort of on average captures 50% of the error. So you're gonna halve the number of errors at every step approximately, so that greatly reduces the number of effective errors. Now, one additional construction is you can say, well, okay, maybe there's some errors you didn't catch yet, maybe a Z error here. So let's add more checks to also check the check qubits. It's just one option. So these we call flag qubits. It's the same construction, right? You have the Hadamard and so on. So here we have the whole setup, and if there's a special case, right? So if this unitary happens at the end of the circuit, then we may not really care about Pauli Z errors at the end, because the measurement is invariant to them. So we only need to check for X and Y errors. So we can use Pauli Z checks here at the end. But it turns out that if you do these checks here at the end with Pauli Z, you can implement them classically. So let's first introduce some Hadamard gates here in the middle, right? So this is just identities. And then you observe that Hadamard times a Pauli control Z is just a C0, right? But if you have a C0 on the qubits, you can also measure them first in the new classical C0, right? If you measure 1 here, then you just negate the outcome there. So that allows you to get rid of this entire block as soon as you start with the random Pauli Z's at the end, and then of course you have to find the corresponding else that match it. So you can get rid of that, And this is kind of an interesting situation where you can apply all the checks and even measure these qubits before, and then run the whole unitary, and then measure, and then still detect the errors, which is very interesting. So this removes idle time between the left and right checks. And it also allows you to include the readout error as part of your payload error. So that's an additional advantage there. Yeah.
Are you imagining U to always be the entire algorithm, the whole circuit, or pieces of the circuit?
Pieces, yeah, usually pieces. It has to be Clifford blocks. If the whole circuit is Clifford, of course, we wouldn't.
So you just isolate the Clifford portion. Yeah, I see.
Yeah, maybe at the end you can have some big basis change to measure a lot of different Paulis at the same time. So that's an option. Yeah. But you can also imagine there's layers of Clifford gates and then non-Clifford gates, etc. Yeah. So far we've just completely ignored qubit connectivity. Just you do any controlled Pauli on any pair, which is not usually realistic, at least for superconducting. So in a more realistic setting, for us at least, we can only access nearest neighbor connectivity. So if we want to apply a CNOT, the qubits have to be physically connected. So how we then implement it is as follows. We start with the data qubits, so this is where our unitary U applies to, and our check qubits. And we then apply the little Pauli component for the check, and we do a swap. So you can just imagine a swap, not just apply the swap gate, but you can just imagine you change the wires logically, right? And then you apply the second part, and you swap again, and the third part. So on the first data qubit, we've applied all of the 3 different checks, and you do this for all of them. Then over here you can apply the unitary U, and then on the other side you do the reverse with different right checks, and then at the end you're back in your original qubit locations, but you've applied the whole check circuit. And as you see here, this is all nearest neighbor. So this is just a line of qubits, and you can only access the previous and the next qubit. So what's the advantage of doing this, aside from that we have to do something local because we cannot just apply arbitrary controlled Pauli gates? If you have a CNOT followed by a swap, that's actually, the swap is just 3 CNOTs. So clearly you can cancel the first one and you just end up with 2 CNOTs. So that's actually cheaper. The same if you have a controlled Pauli Z plus a swap, you can implement it with two qubit gates, and likewise for Y. The only controlled check you cannot do with 2 is the controlled identity, which now takes a swap, which is actually 3 Pauli, so that's more expensive. But otherwise, you do reduce the number of gates. You can do a similar construction to implement these flags on top of the check qubits, but it just requires you to interleave the flags and the qubits at the beginning, and then just apply the circuit to split them up and just keep going like that. So let's look at the analysis of this method, right? So there's 2 quantities of importance. One is the post-selection rate that was already mentioned. How many of your shots actually survive this check, right? This will go down with the number of checks. So if 1 per million survives, then of course you need to take an awful lot of samples to get any information out. The second one is, what is the logical error rate? So given the shots that do survive, how many of those are still wrong? So after the filtering. So to analyze this model, we formulated it as a Markov model. We just assume 2 qubit depolarizing errors on CNOT gates, and no errors right now on the readout or during the idle time, right? And for Pauli checks, because we sample them at random, we just say there's an independent detection rate of 50% per check on the error, so there's no correlations there. Okay, so what does the model look like? So the model consists of the probabilities of a detected error. So I've already detected that there was an error, and I'm going to definitely throw away the shot. There's an undetected error. So there was an error, but we didn't detect it, or there was just no error at all. Right? And if you just look at the innermost parts, just apply the payload circuit U, then there's no detected errors. There's epsilon payload errors that are the errors in the payload, and 1 minus epsilon of no errors at all. Right? Per check, so that's left and right or just left, you have a chance that there was no errors in the check at all. Right? The check can also have a error by itself, just by the controlled Pauli operations. And sometimes these can be detected by itself as well. So let's say there's a detected error, and then there's an undetected error, which is just all the rest of the probability mass. Then it turns out that if you add one check, you can update the probability vector with some matrix that looks like this. Right? This is just if you were okay, there was no error, you stay there. If there was an undetected error, and there's an undetected error in the check, let's see, you map to the undetected error, plus there's a chance that there was an error actually, but you didn't detect it with a 50% chance. So this is the way you update your system. And then we want to look at the post-selection and the logical error rates, right? So for a given state. So post-selection is just you select everything that either has an undetected error or no error. So you just get rid of your detected errors pretty much. The logical error rate is amongst those, which one has an error. That's just the undetected error. So this pi2 divided by pi2 plus pi3. That gives you the logical error rate after this process. Okay, so every 2-qubit gate used in this construction has some epsilon depolarizing noise given by this, right? So either there's no error or each of the Paulis has the same probability of occurring. A detectable error here will be half of those Paulis, right? So just 8 epsilon over 15. For each of the gates, right? So if you have k gates to implement your check, then the probability that there's no error is 1 minus epsilon to the power k. That's just no error at all. So then you can look at what is the chance of having a detected error, and that turns out that if you have one detected error, then it would flip the sign, but the measurement from 0 to 1. But if you have yet another detectable error, it will cancel it out. It will switch it off again. So it's just a summation over the number of odd number of detectable errors. How many ways can you find L of those gates to be wrong, etc. And that gives you an expression for this TD. Right? Then how many gates are there for random checks? So some of them may have identity, some may have Pauli X, Y, Z, etc. What is the expected number of checks in a fully connected left and right checks? That's given by this. Fully connected left only, linear, that's just the construction I showed earlier. How many checks? You see you have more gates in this case than fully connected, but it's still linear in the number of qubits. Okay, so if you plug in all of these numbers, you can look at the asymptotic logical error rate by just looking at the eigenvalues of this transition matrix, right? So asymptotically, if the probability of applying the check does not have an error that's bigger than a half, so it's a reasonable check, let's say, and the payload error is less than 1, then asymptotically you can reach this logical error rate. Otherwise, it will just be 1. It will just get worse. If your check introduces more errors than it can detect, then it will just get worse by adding more checks. The post-selection rate always decreases by every check, so between a factor and half and this TU plus TOK. And towards steady state, this rate will decrease by TOK. So if your gates to do the check are pretty good, that gives the overall rate of decreasing of the post-selection rate. Okay, so let's just do a numerical simulation, right? So these are Clifford circuits. So we can represent Pauli's by binary vectors of length 2n. So you have an x component and a z component, and if you have x and z, you have a y Pauli. If you have neither x nor z, you have identity, etc. Then you can represent your state with some binary matrix. And actually, we use the same formalism to propagate errors. So every row in this matrix will represent a sampled error. Then there's operations on this on this tableau of bits that correspond to moving, applying a Clifford operation. So you can do that for every operation, and then after each gate or before, you can say I'm going to add sample noise and insert that into the tableau as well. So you can really sample what are the noise outcomes of your tableau. You don't really need to take shots at that point, because you know if there is an x or a y term before your measurement, before your check measurement, you know it's going to be flipped, and you know originally it's supposed to be 0, so you know you would measure a 1. So you know if it was affected by an error. So if you do that for different settings, you can compute the empirical post-selection and logical error rates. You know if there was an error, you know if it was detected, so you take a lot of samples and you just calculate it. So that's here. This is the theory versus the simulation. So we just randomly sampled a 20-qubit Clifford circuit, then added depolarizing noise on each of the gates. And for the simulation, we just generate 10,000 shots, just sample it, right, and see what you get. So the dots here are all of the simulated values. So you get a logical error rate and a number of checks, and the dots show the behavior. The solid lines here is just the evolution of your initial state by this transition matrix. So that matches the data very nicely. And asymptotics is the dashed line. So with those settings, if you have fully connected you have checks on both left and right on a linear topology, then in this setting your error cannot be below this value. If you add more and more checks, you can approach it, but you cannot go below it. And you see all to all that has better results. And if you have the half version of just one side, you can get much lower logical error rates. Now, this is of course one issue is the post-selection rate. So the number of checks, you always lose more and more shots. You can never get better in that sense. And this rate was this TOK at the end, and initially it goes down by a factor of a half, and then just slowly goes towards this TOK. So at this point, if you 20 checks, then maybe one every 10,000 shots you will actually keep. So there's a lot of overhead there. For the other settings, this is a lot better. One every 100 may be acceptable. This is just another plot of the logical error rate versus 1 over the post-selection rate. So you see that if you want to decrease the post-selection rate, decrease the logical error rate, this is sort of the number of shots, right, or the overhead. So that goes towards infinity then, if you really want to push it closer. Then some experiments. This is on the device called IBM Washington. We just chose some lines of qubits, right? There's just some statistics, some information there of the T1 and T2, etc. And then we're just gonna use those lines of qubits to apply this Pauli checks. So this is just a one-sided experiment. The payload is very simple. We just repeat CNOTs on certain gates 48 times, so it's not really a useful circuit, but we know what the outcome should be. Then per setting, we do 10 random instances of these left and right Paulis. Right? And then take a lot of shots just to make sure that even at a large number of checks, we get some results. Of course, the variation here will be bigger because there's fewer actual samples that survive. So for 2 qubits, you see that the logical error rate was not too high to start with, but it really shrinks. 4 qubits, it also decreases a lot. And those curves may just need a lot more checks for 10 qubits to make this work. So that's just how many shots do you want to take. This is just the second chain. This is the same behavior, just different curves. And this is the post-selection rate. So you see it does go down to some smaller number, 1 every 10,000 samples in this setting. For the 2 qubit or 4 qubit, that's fairly manageable. This is just the same for the second chain. And here's just a table that shows the logical error rate with no checks, the logical error rate with 15 checks, and the post-selection rate. So these error rates do drop dramatically in this setting. Here you may need more checks to really suppress it. Yes?
In the case where the depolarizing noise, or I guess the gate noise is too high, would the error rate increase instead of decrease as I add more checks? Because each check introduces more errors than you can correct for, or detect for?
Yeah, so if the overall error of applying the check is less than a half, it will go down. But the asymptotic value to which it goes down depends on that value as well. It might just go down a little bit. But if you can apply a check with very little error overall, then it has much more potential to go down.
I see. So there's not really a stringent threshold in the same way that QEC does, where I really need the error rate to be 1%-ish.
No. But of course, if the error is too large and implementing check is close to a half, or 50-50 being right or wrong, then you don't gain much.
I see.
Yeah. And also the asymptotic error rate drops by that factor, so it might half every time you add a check. That decreases exponentially.
I see.
Yeah.
These are dense circuits. Like literally, you have a CNOT, CNOT, CNOT.
Yeah, just dense. Yeah.
So if you had, say, 8 qubits but half the number of CNOTs, would you see the same performance as 4 there, or it doesn't quite work that way?
This is just the same dense circuit, but for more qubits. Right? And every time you add 2 qubits, you add another CNOT.
Right. But if you lowered the density, would you get better performance at larger numbers of qubits, or it doesn't quite work?
Well, in a way, if your payload would be noiseless, then you can almost only make it worse. So yeah, there will be some balance there. Yeah.
Well, is this error rate like a state preparation and measure type of error rate, like a quantum memory type of experiment, or is it more like gadgets, gate type of error rate?
But this in a way doesn't really depend on the initial state, right? So the state preparation doesn't really matter. But of course, if you measure there will be measurement error. So if you measure the check qubit and it's supposed to be 1, but you measure 0, then you wouldn't detect it.
So this is a gate error rate.
Yeah, but then it does apply to the measurement as well. Yeah.
So what would be the theory like if you have some of these Cliffords and then mingled with non-Clifford? So you use
Well, so with the problem, just like PEC with non-Clifford, is that if you have two left Paulis and you want to push it through the
right.
payload circuit, which is not Clifford, it will split up into two terms.
Yeah,
Or multiple.
we just apply this coherent checks on the Clifford. Non-Cliffords, I don't know of any methods like this to do it, so like we just leave them as it is.
Yeah, those if you would apply this to only Clifford subcircuits, then that's what you would do. Yeah, just this technique by itself.
So like the kind of scaling, all of this doesn't change in that picture.
So of course, if there's errors in the not non-Clifford gates, you wouldn't detect those.
Right.
Because they're just outside of the scope. They're just inside your row, and you see the whole circuits of left, right. You have some initial state. You don't really care what the initial state was.
Okay.
Yeah.
So I guess the kind of acceptance rate will kind of is proportional to like exponential of the number of these blocks of Cliffords.
Yeah. So if you would apply the same techniques with some non-Clifford gates in the circuit outside of the checks, right? The acceptance rate would be the same, because you just check that part of the circuit. But of course the undetected errors would get larger because you don't detect the errors outside of this check. So then the logical error rate would still go up. Okay, so this gives some good improvements for this number of qubits with still reasonable post-selection rates. This is just another setting where you just do EPR pair initialization. Then this circuit is a random permutation, so you expect sort of longer distance ERP pairs to measure those. And I think, I'm not sure if this was the logical error rate, but again, up to, let's say, six qubits, it still goes down, then it doesn't really do much. This is just for the other chain. Post-selection rates. And just a summary, right, of this setting, how many payload CNOTs there are, and so on. Because this is a random permutation, that takes a lot of gates to implement. So the error rate there will be pretty large to start with. And this is just a reduction again, maybe from 80% to 50%. So it's substantial, but it doesn't really, it doesn't make the errors go away altogether. Now this is something we notice, right? This is a one-sided check for 4, 6, and 8 qubits. But if we now apply two-sided checks, it just seemed to make things worse, right? And why is that? And that actually, I just attribute this to idle time, right? So you have your unitary here with your checks. Between these checks, this qubit is just sitting there doing nothing. You can apply dynamical decoupling, maybe make things a little better, but it's just sitting there decohering, and that will affect this approach. So this is one of the downsides of this approach. And especially if the circuit is very long, right, a very deep Clifford circuit, then this may deteriorate the performance. So to analyze this in more detail of really pinpointing this to the idle time, we did another more realistic modeling of the circuit. So first of all, you also add readout errors and the idle time. And once you've modeled this, you can then evaluate the logical error rate and post-selection rate. So we just get some noise model from the backend and convert it to Pauli noise, right? Then we generate the circuit and transpile it to basis gates, so the gates that are really supported on the hardware, and then you need to schedule them. At what time are they executed? While doing this, you still want to keep track of which gate and which delay belongs to which check. And well, now we have a bigger circuit, so we cannot really say the error rate of the circuit is something. We just need to find some bounds on the error rate. Then you just propagate the errors through the circuit and use a slightly bigger Markovian model that models this. And it's a little harder to update because you really have so many gates flying around everywhere. We can then scale the different noise levels to check what the effect of this is. Right? So here's a all-to-all connectivity. That's just a simulation, obviously. What we do here in the columns A, B, and C is to scale the T1 and T2 values by 0.2. So this is better T. We divide it by 0.2, so that the T1 time is 5 times longer. And this is sort of the baseline T1. Then we just simulate everything. Let's see what we have here. This is the logical error rate and the post-selection rate. The dots are the simulated ones. It's just by the tableau, etc. And the lines are again the Markov model. So they still match very well here. We have settings where you just have checks and flags and the left only setting without flags. So from the analysis, we know that there's more approximations in the flag setting, so that sometimes deviates, but the other ones are pretty good. Now, if you sort of decrease the T1 time, then you see that this reduction in error rate is not as pronounced, except for the left side only check, because there's no idle wait time between the check and the measurement. But in the other two settings, the error rate gets worse because you just spend so much time doing nothing in between with number of checks that you introduce more errors than you get out. And this also has an effect on the post-selection rates, which just decreases much faster in this case because the error is just bigger. This is the same setting in the nearest neighbor linear approach. The picture is pretty much the same, right? These curves get a little worse. This is if we scale the noise on the C-naughts and the delay term, so the T1, T2, by different factors. And I think there's another parameter here. This is just how much do you scale the C-naught and how much do you scale the delay. So here there's no error on the delay and get some better results. So you can actually also apply this for checks on the readout. So if you imagine we're going to just measure anything, we can just put a virtual identity Clifford circuit and then just apply the whole machinery. And that turns out to just apply a C-naught before and a C-naught after. If you repeat this several times, what actually happens is that you start to implement a repetition code on the readout. So if you're going to measure 0 here, you also want to measure 0 here and here, and then you can look at the outcomes and sort of improve the readout. So you can use this one-sided check at the end of the circuit to include the readout error as part of the payload error. And then based on the outcome, you can say, well, I want all of the measured bits to be identical, or you can do some majority voting, right? So identical is unanimous. Every measurement has to agree that this is much more stringent. So we again model this with some target error and control error plus some measurement error on each of the gates. So then what we can do is we can look at as a function of C-naught error and the readout error per combination, we can see what is the overall readout error as a color and just some isolines. So if there's no checks, of course, if the readout error is 8%, let's say, then irrespective of your C-naught error, it will stay 8%. That's obviously. But if you then do one check, you get much different behavior. Even if the readout error is 9%, you depending on the quality of the C0 error, if there's no C0 error, you get 1% here pretty much, and that's just the ISO curve. In this area here, if the C0 error is too big, you introduce more errors than the readout error to start with. So then, of course, that's a region where you don't want to try this. And this improves with 2 checks, and again, you can do more checks, and asymptotically, you would get these curves for the readout error. So the per qubit readout error can actually be quite large. As long as the C0 error is not too big, you can still get good readout in this model. So this is just again an experiment here. I think just the measurement error rates in percentage. I forgot what is the first and the second column. Oh, if you measure them individually versus all simultaneous, and what is the approximate C0 error rate. So then these are the curves it gets. So this is the logical error rate of the measurement. It starts here, and you add more checks, and if you do unanimous decoding, it goes down to some point, and it doesn't really move much beyond that. The post-selection rate here does go down. If you do majority voting, right, this kind of only applies for odd numbers of measurements. Then actually the logical error rate increases again, but the post-selection rate is pretty much all one, except for the even number, because if you measure 2, there's no clear winner. If you measure 0 and 1, you don't know which one you have to do. So you have to throw out ties in that case. So if we just increase the readout error artificially a little bit, you see that the majority voting does decrease the actual logical error rate, but not as much as unanimous, but unanimous has a much slower post-selection rate.
So is that a direct trade-off of the C0 error directly, which is creating the repetition, versus the readout error itself? Readout error.
This would also be the case without, well, no, with the C0 error. If there's no C0 error and you measure them independently, then this is just the probability of getting all of them right versus several of them, right? Yeah. Yeah, great.
Do we know why the logical error rate kind of plateaus to a steady state value instead of decreasing arbitrarily as we increase the number of checks?
I think that it must sort of plateau at the C0 error rate, more or less. But I'm not exactly sure why it levels off right here. Yeah. So yeah, I think that's also, we just went over the noise channels, noisy gates, readout error mitigation, noise learning, and then use those techniques for the probabilistic error cancellation, zero noise extrapolation, based on the probabilistic error amplification, which used the same noise model. And then we looked at the coherent Pauli checks method, which is not so much aimed at observable values, but more individual shots. So thank you very much.